The capacitance of a uniform sphere of radius 10 km is nearly. Equation for capacitance is 4 pi epsilon 0 r for a uniform sphere. We already know that charge is equal to Q equal to CV. From this we can derive the equation C equal to Q by V. Q divided by V is actually 1 by 4 pi epsilon 0 Q by R. So this will get cancelled so that it will go to the numerator. You will get 4 pi epsilon 0 R. Here value of 4 pi epsilon 0 is 1 by 9 into 10 raised to 9 and R is 10 kilometers, that is 10 into 10 raised to 3 meters. So when you calculate this you will get 10 divided by 9, that is 1.1 into 10 raised to minus 6, or you will get 1.1 microfarad. Equivalent capacitance between A and B. Here in this network, three capacitors are there. From A, one capacitor is connected. First one. The end is connected to the second one and also to B. End is connected to second one and also to B. And from B, there is a third capacitor. From B, there is a third capacitor. The end of the third one is connected to A. End of third one is connected to A. And see, the end of second one, the end of second one is connected to the third one, is connected to the third one. Third one is going here. So between A and B, actually we have three capacitors, 1, 2, 3. They are in parallel. In parallel connection, total capacitance is sum of all. So here 3 are there. So C plus C plus C, that is 3C. Option C is the correct one. Equivalent capacitance between A and B. Here between A and B, in this network, these three capacitors are in series. So in series connection, if the capacitors are equal, we can write the effective capacitance as C by N. Here capacitance value is 3C and number of capacitors are 3. So we will get C. And let us consider these 2C capacitors. They are also in series. So we can write the equation as C by N itself. Here capacitance is 2C and number of capacitors are 2. So effective capacitance again C. And let us consider these two combinations. These two are connected in parallel. So in parallel connection, effective capacitance we can write as sum of all. Here C plus C, that is 2C. Equation option A is the correct one. A parallel plate capacitor has a capacitance of 5 microfarad. On introducing a conducting slab of thickness equal to 1/2 of the distance between the plates, the capacitance now becomes. For a parallel plate capacitor, the capacitance is epsilon 0 A by D and its value is given as 5 microfarad, where D is the distance between the plate and A is the area of the plate. When you introduce a dielectric slab of thickness D by 2, its capacitance value also changes. That is, equation becomes C equal to epsilon 0 A divided by D minus T, where T is the thickness of the slab. That is epsilon 0 A by D minus T is D by 2. So this becomes epsilon 0 A divided by D minus D by 2 is D by 2 itself. So you will get epsilon 0 A divided by D into 2. That is 2 times this value. That is 2 into, we already know that epsilon 0 A by D is 5 microfarad. So 2 into 5 microfarad, you will get 10 microfarad as the answer. Option C is the correct. The capacitance of a capacitor capable of storing 2 joule of energy when used with a 100 volt DC supply is. Options are given. Equation for energy stored in a capacitor is E is equal to half CV square. Here energy is given as 2 joule, that is equal to half into C into potential is given as 100 volt. So it is 100 square. From this we will get C as 2 into 2 divided by 100 square, or you can write it as 4 by this much, or when you multiply by 100 by 100 you will get 400 microfarad. So correct option is option C. A parallel plate capacitor with each plate of area A separated by a distance D is filled with dielectric of dielectric constant K1 equal to 2, K2 equal to 4 as shown. The effective capacitance is now, we know that for a parallel plate capacitor, capacitance is epsilon 0 A by D, where A is the plate area, D is the plate separation. Here in this capacitor, two dielectrics are there, K1 and K2. So here the plate area becomes half for both. For the first one also plate area is A by 2. For the second one also plate area is A by 2, because we are dividing it into half. So for the first half, capacitance is K1 epsilon 0 A by 2 divided by D, same for both D. And for the second half, C2 equal to K2 into epsilon 0 A by 2 divided by D. D is same for both. Plate separation is not changing. And these two capacitors we can say as they are in parallel. They are like parallel connection. So we can write the effective capacitance as C1 plus C2, sum of 2. That is K1 epsilon 0 A divided by 2D plus K2 epsilon 0 A divided by 2D. Or we can write it as epsilon 0 A by D into K1 plus K2. 2D into K1 plus K2. That is epsilon 0 A by 2D into K1 is 2, K2 is 4. So we will get epsilon 0 A divided by 2D into 6, or we will get 3 epsilon 0 A by D. So correct option is option A. Effective capacitance between A and B is. Here let us first consider the 4 capacitors, and these 4 capacitors are like a balanced Wheatstone bridge, so that there will not be a current flow through this capacitor. So this can be eliminated and we can draw the network like this. We can redraw it like this. And the middle one we have neglected because there is no current flow through that. And now we know that these two are in series connection. So, and they are equal also. So in series connection, effective capacitance is C by N. here C divided by, there are two capacitors. So again, when we consider these two, effective capacitance is C by N. Here capacitance is C and N is 2, and here the capacitance is C. So all these three are again connected in parallel. These two, and the last one is connected in parallel. So we can write in parallel circuit, the effective capacitance is the sum of all, that is C by 2 plus C by 2 plus C, that is C plus C, that is 2C. So option B is the correct one.